Hello, everyone. My name is Dan Croats, and I'm with the Public Affairs here. And thanks for attending our second installment of Sit Down with Sabin, which is a new spin on our summer lecture series. Over the course of the next several weeks, Sabin will engage lab staff about the ins and outs and ups and downs of innovative science. Last week it was the hunt for dark energy. Today it's going to be the future of batteries. And next week, if I'm not mistaken, it's about the carbon cycle. But we also definitely want to hear from you, so there'll be plenty of time for questions throughout the talk to ask questions of the panelists. One of the first questions you might have, and I'll answer that now, is who is Sabin Russell? Our moderator. Sabin joined Berkeley Lab only last year after a very long and illustrious career as a Bay Area health and science reporter. This included 22 years at the San Francisco Chronicle, freelance work for the New York Times, as well as a Knight Science Journalism Fellowship at MIT. During this time, he was best known for his work covering HIV in both the US and Africa, as well as the Columbia shuttle disaster and the tsunami in Sri Lanka. He is now up for hire here at Berkeley Lab. We're very happy to have him as the lead editor and writer for the Creative Services Office, which is a public affairs unit that writes, edits, and produces documents and web products throughout the lab. So he's available for hire, and you could grab him afterwards if you want to chat about other possibilities. With that, and without any further ado, the stage is now yours, Sabin.
Thank you, Dan. When I joined this lab a year ago, one of the things that struck me almost from the day one was the diversity of science that goes on in this place. We've got nanotechnologists at the molecular foundry. We have cosmologists in this building here. We have high-energy physics people doing work at the ALS and at some of the cyclotrons. And we have, over in Building 90, people working on the Darfur stove. It's an amazing place, and one of the purposes of this event is to open the lab up to all of us, to people from different parts of the campus, to come and listen to science. The one thing we all have in common is an interest in science, and what I want to do here is kind of celebrate what's new and interesting and important at this lab. Our topic today is batteries, and it fits all three categories of new and interesting and important. And although we are not permitting PowerPoints as a kind of discipline we are imposing on this format, we are allowed to bring props. And so I thought I would bring this prop that I got from Sunday. This is the first edition of the new News of the Week and Review section of the New York Times. And look at the amount of real estate they're devoting to what is a battery for the Chevy Volt. Somebody in New York feels that batteries are important. And so it gives me a great pleasure to introduce our guest, Venkat Srinivasan. When the New York Times is writing an article about batteries, or most recently in the current issue of Science, one of the go-to people they call for quotes is Venkat. He's a leading expert in batteries, particularly transportation batteries. He is the acting director of the Batteries for Advanced Transportation Technologies, BATT. Get it? That's a smart folks here. That's a Department of Energy program that's been going on for a long time. Venkat hails from near Chennai, India. He got his BA at the Central Electrochemical Research Institute in Karaikudi, India. He got his PhD at the University of South Carolina. He came to Berkeley Lab as a postdoc in 2003, and now he's a staff scientist with EETD. It gives me a great pleasure to introduce to you Venkat Srinivasan.
Thank you.
I should also mention that in addition to his distinguished work as a battery scientist and engineer, Venkat is also a blogger. He is the blogger for a site that he originally called, or maybe you're still calling it, This Week in Batteries. You can now, we'll be talking about his blogging during our discussion, You can look it up now on a new site called GigaOM or GigaOM. It's spelled as it sounds. We can talk about that later. But let's talk now about why batteries are important, Venkat. And one of the things that sort of strikes me is we're all familiar, I think, here with Moore's law in electronics, which, according to the Intel website, says that the number of transistors that you can cram onto a chip doubles every 2 years. And that curve has driven so much of our progress in electronics today. Our whole society is largely shaped by electronics now. And so we have this very steep curve called Moore's law. And yet, there seems to be a bottleneck when we're talking about electricity and electronics in progress, and that happens to be batteries. So I guess my first question to you, Venkat, is, where are you guys screwing up?
Exactly. So let me say one thing before we get into the Moore's law for batteries. I think you were talking about me being the go-to guy for the New York Times. So I was a battery scientist for 15 years. Nobody knew who I was. I write 2 blog posts, and the New York Times starts calling me, right? So it kind of gives you a perspective of what you ought to be doing. You may be wanting to go to the web more than writing papers, I guess. So going back to the Moore's law, just so everybody's level set, the evolution of batteries is approximately 5 to 6% a year. And what I'm talking about is energy density. What I mean by that is how much energy can you pack into a small battery, a battery that you may have in your laptop or your cell phone. So that improves by approximately 5 or 6%, and sort of the comparison to the doubling of energy density every 2 years, that's where people get all hung up on why is it that batteries are screwing up. So I sort of wrote a blog post on this probably a year and a half ago, and let me try to remind myself of what I wrote. The first thing you have to think about, right, when you think about electronics, what you're trying to do in Moore's law is you're trying to use better lithography tools to make more and more whatever transistors in the same given space. And so tools have gotten better, and they're evolving every generation to a point where you have smaller and smaller devices that are packed in, so that the same volume can accommodate a lot more of these devices, right? So the equivalent for batteries would be, I have a box, I have a bunch of anodes and cathodes, which we'll talk about at some point, that I have to pack into the box. So the question is, how much of the anode and the cathode can I pack in? So if I keep packing in more and more and more, I keep evolving in batteries. We've been doing that for many years, turns out for 100 years. And there's only so much you can pack in. At some point, you get to a limit where you can't pack in anymore. And you do that, you have to find new materials, materials that are intrinsically higher energy, so that you can pack them in the same amount and get more energy from the battery. In the semiconductor space, this is like saying you have to come up with a brand new material, not silicon. And every year, you have to come up with a brand new material. And that's the only way to evolve. If semiconductors were to reach that point, you can imagine that things will be slower, because trying to find a new material is very hard. And that's what is happening in batteries. For us to evolve in batteries, we have to find a new material every time. And finding a new material is very, very hard in the battery space, and in many other spaces, as it turns out.
So we have with batteries not a sort of an apples and oranges comparison then.
Correct.
To Moore's law.
Correct.
Regardless of that metaphor, what we do have is a problem. We do need batteries. One of the reasons there's so much attention being paid to it is that batteries seem to be the weak link in the chain on a number of technologies that are becoming essential for us, such as electric cars, such as storage of alternative energy sources such as wind and photovoltaics, and also, frankly, for electronic devices. We are frequently carrying very small electronic devices, and most of the weight that we're carrying around, as I understand it, is batteries.
Yes.
So if we were to kind of break down the problems and the challenges that are facing battery technology for the future, what are the key components? You've mentioned materials, but there are other factors. There are, I understand, 4 different metrics on which batteries are often measured, and how does the current technology stack up with them?
Right. So I mean, that's another big difference between semiconductors and sort of chemistry, right? In a battery, you need energy, which tells you how long you can drive an electric car. You need power that tells you how quickly you can go from, say, 0 to 60. But you have to have long life, meaning a battery has to go 10 years, maybe even 15 years. You've got to get decent performance even at low temperatures. It's got to be safe. And on top of all that, it's got to cost you, next to nothing. So that's, there are multiple things that are sort of playing with. And it turns out that people like us try to show these spider graphs that have all these different axes. And in batteries, it's kind of interesting. If you ever pull on one axis, meaning if I try to make one of those metrics better, something else seems to go worse. So it sort of has this multi-dimensional problem that we're talking about, right? If you ask me what are the biggest challenges we face in the world, and I'm going to forget consumer electronics for the time being, just because let's think about electric vehicles. There are two very large problems. First is we've got to make batteries more cost-effective, meaning they've got to be a lot cheaper than they are today. Just to give you an example, the Chevy Volt battery, the one you showed, is probably like $16,000.
16.
1.6. So think about it, right? You're going to pay for the Chevy Cruze or whatever car you're buying, and then you're going to buy an extra $16,000 for the battery pack, because that's what the Chevy Volt is. It's a car plus a battery pack, right? And I'm being simplistic here, but you kind of get the idea.
It's also realistic.
Exactly. I mean, so these are the kind of numbers that people are talking about. The Tesla Roadster's battery costs $25,000. So that's a lot of money. So what we have to think about is how you're going to decrease these costs down to maybe $6,000 or maybe even $5,000. If you can do that, then you can have a dramatic increase. But there is a second aspect to this, which is sort of the difference between a Chevy Volt and a Nissan Leaf. A Chevy Volt is a plug-in hybrid car, meaning that you have a gasoline tank and you have a battery pack. The Nissan Leaf is a pure electric car. The Nissan Leaf driving range is approximately, depending upon how you count, 70 miles to 100 miles. And for some people, that is just not enough. And so there is a segment of the population that believes that they need a 300-mile car. Now, people in Berkeley don't need that. I mean, all of you are very environmentally conscious, and you only need a car that goes maybe 10 miles. But there are a lot of people out there who say they want a car like a gasoline car. That brings up a big different problem, which is that we don't have the energy density to be able to pack a lot of batteries in a very small volume, which means that we'll have to increase the energy density pretty significantly.
So this concept of energy density is very, very important if you're trying to understand where batteries need to go.
Yes.
For instance, we're talking about energy density in a battery, but the term could also apply to gasoline.
Yes.
Gasoline, I presume, must have a very favorable energy density.
Yes. So if you make a comparison, and let's be careful of these numbers. The energy content of gasoline, you have to then put in there's a Carnot efficiency, so you got to do all that, right? But let me just throw a ballpark figure. There's an approximately a factor of 20 difference between a battery pack and gasoline in a tank. So we are at approximately 200 watt-hours per kilogram. A gasoline tank would be 4,000. So a factor of 10 is 2,000, so a factor of 20. So to imagine that all of a sudden batteries are going to go, and remember I told you batteries evolve at 5-6%, right? So that's the historical average. So to imagine that we're going to go from 200 to 4,000 anytime soon is probably not the right way to think about it. I like to think about it differently. I like to think about it as, what do you need to make an electric car successful? And you do not need 20 times increase in energy density to make it successful. What you need is maybe a battery that costs half of what it costs today, and maybe a battery that has twice the energy of what you have today, somewhere there. Others have a different view. Some might say you have to go larger. We can argue about that. But one wants to think of what is realistically possible and where you want to go and what you need to have, I think.
So despite the doom and gloom of the fact that batteries represent this bottleneck right now, I get a sense from you that there is some reason for optimism
Yes.
in the research right now.
Yes.
And in fact, if you were to read some of the articles that are out there right now about batteries, there is an excitement in the air
Yes.
about battery research right now.
Yes.
Because of things that are happening in the lab and the possibilities that may be opening. Tell us about some of those developments.
Right. So obviously for many years we were using different chemistries like lead acid batteries and nickel metal hydride. In the early 1990s, we all moved to lithium batteries. And a lithium battery is not one single battery. It actually consists of a multitude of anodes and cathodes that you can sort of plug and play. And depending upon the anode and the cathode, you can change everything in the battery, meaning you can change the energy, the power, the cost, the life. And it turns out that actively we're all, including the people at Berkeley, we're all looking at new materials that pack in a lot of electrons for the same weight and volume. And when you pack in a lot of electrons, in some sense you have a more higher energy battery than what you have before, right? So people like me believe, looking at just what is happening in the space today, that in the next few years, and I'm not going to define few, but in the next few years, we'll have a doubling of energy density compared to where we are today.
A doubling?
A doubling. Now think about that. That's a pretty significant increase.
Absolutely.
Now, there was a person that I was talking to from CNET, which is one of the consumer sort of the electronics world, And she immediately said, oh, does that mean my iPhone is going to last twice as long? And I was like, you got to be careful. My suspicion is your iPhone is probably last as much at the same time because they'll put more software into it that drains the battery more. But an electric car is a different story, right? I mean, in the sense that if you're willing to live with cars that are as small as a Nissan Leaf, that means that we can actually go twice as much on the same space of the battery than we can do today. And that's a pretty significant step, right? Mm-hmm. Let's talk about cost a little bit, right? It turns out 50% of battery costs are manufacturing costs. The other 50% are material costs, right? So people like me are always thinking about cheap materials, but there are people in the industrial world that are thinking about making industrial batteries a little bit cheaper, thinking about all those aspects of it, right? Turns out that in the United States, or even in the rest of the world, there is no real mass manufacturing of batteries for electric cars. So there's mass manufacturing of batteries for consumer electronic applications, but the batteries for consumer electronics are very different from batteries for cars, and there is no mass manufacturing of batteries for cars.
So you're saying that the batteries that are going into the Priuses and the Volts and the Leafs are more or less hand-built?
No, the Priuses are different. So that's a different class of batteries, and so those are not hand-built. But the Volt and the Leaf are all built in very small factories where you haven't really paid down the capital cost of all the equipment that you've bought. So that's going to give you a little bit of reduction in cost. Maybe not all the way to where we can all be buying this cheap, free or cheap or whatever, but it's going to give us a reduction in cost. And that's going to be the first step towards getting a cheaper battery. And then there's going to be evolution in these chemistries. There's going to be new ways of processing the battery material so that they're cheaper than what we're doing today. And I'm one of those who's really hopeful that we will see a reasonable decrease in cost and a reasonable increase in energy density where these systems will start becoming reasonably competitive.
Now, in this conversational format with our diverse audience, which includes students as well as staff scientists, we're not going to go too deep with the science, but we do talk a lot about anodes and cathodes, and so I brought another prop.
He's substituting for the fact that I don't bring any props, I guess. But.
And so there are two parts to a battery. And not only is this a visual aid, I have a mnemonic aid, Venkat cathode. And I'm the other guy.
So I have to say something here.
And here we have water, the electrolyte.
It's a very poor one, but. So one thing I do have to say here, right? It turns out that 10 years ago, if you had told anybody that in a battery you have an anode and a cathode, they would have said, I'm sorry, that's just completely wrong. Because it turns out in a battery, an anode and a cathode keep switching on each other. But in the last 10 years, battery people have forgotten all those rules. And nobody calls it negative and positive anymore. Everybody calls it a cathode for a positive electrode, an anode for a negative electrode. So you were perfectly right in your terminology. Your symbols, I guess, are going back to the older days of batteries, I guess.
And when you say everybody, you're talking about everybody who knows something about batteries, which is not very many people.
It turns out the general public still gets confused when we use the word cathode and anode, but battery people just use it as if that's the norm. And actually, the general public is right. The scientists are wrong about this.
Right. So what sort of, we're talking a lot about lithium. We've talked earlier about the earlier generation of nickel hydride. We talk about lead acid, and here we're all talking about rechargeable batteries. Maybe we'll talk about the batteries that are not rechargeable, but I think for the purposes of the future, we're really talking rechargeable battery technology. We're now talking a lot about lithium. So I'm wondering, I mean, what is it in a material that makes it a suitable one for a battery? The periodic table is very large. But there's really only a handful of materials that turn up again and again as useful in batteries. What traits are you looking for in materials for batteries?
So you are right. One can literally go to the periodic table. So all you're looking for in a battery is a material that oxidizes easily and a material that reduces easily. You put them together, you have a battery, in effect. Okay. You can go to the periodic table. You can go pick up two metals. You'll probably make a battery with it. Actually, it's pretty easy. You can do it in high school. Lemon batteries are essentially that. You're picking two metals, putting them aside, and you get a voltage, and you make a battery. So making a battery is actually very easy, but it's very hard to make a good battery, or even a decent battery, right? So it turns out that's why we have very few things that work. And it turns out that all the batteries we know today are not ones where you go just to the periodic table and pull them out. Turns out the ones you pull off the periodic table don't work that well. You have to do something to them. Okay? So let's take lithium batteries as an example, right? So it turns out I wrote a blog post on why do you choose a lithium battery? And it's kind of, you can think of this as a fiction, meaning, think of it as you're sitting in 1950 or 1960, you're thinking about how to make a high energy battery, you go to the periodic table, you go pick up the most electropositive, the most electronegative, and you're saying, I can make a battery with it. So you go to the periodic table, you look at lithium and you say, yeah, that seems like something that I can use. You take fluorine and you think you can use that. Turns out the world's best battery would be a lithium fluorine battery. Nobody wants to work with fluorine, so you give up that concept immediately because that's something you don't want to even touch. And it turns out that lithium is very hard to work with. We've been trying to work with lithium as a metal for many years, and we're still struggling to do that, and we haven't really done that as well as we ought to have done.
And lithium, when it gets near water, is a problem?
Is a problem. Handling it is a problem. It turns out when you're trying to charge them, there is a slight problem that occurs. So rechargeable lithium batteries are hard to make. Primary lithium batteries, your watch battery, has been around for 30, 40 years, but trying to make them rechargeable has been a very big challenge.
So one of the metrics that comes up again and again about batteries, in addition to energy density, is safety.
Yes.
And so when you're trying to pack a lot of energy into a battery, you're automatically playing with something that is potentially dangerous.
Yes. You're putting an oxidant and reductant right next to each other with very little separation, and bad things want to happen. And intrinsically, you have to find ways to control those reactions. A battery is an energy storage device, and the energy can come out spontaneously very fast as heat and do something very bad for you.
So what was it about lithium in particular that has made it the material of choice? We have our electron-hungry cathode, right? And we have an electron-dumping anode over here. Why is it that lithium, perhaps modified lithium, works so well that it's the state of the art right now?
So essentially, the quest for the battery is a quest for a high voltage battery. So what you want to do is you want to increase the voltage of the battery. When you increase the voltage of battery, you get more energy from the battery. So the nickel metal hydride battery uses water as the electrolyte. I mean, it turns out it's potassium hydroxide, but it's a water-based electrolyte. And if you think about water, the reaction that stops water from being used when you go to high voltages is oxidation and reduction of the water itself to make hydrogen and oxygen. So you get essentially an oxygen cycle or a hydrogen cycle. And so that happens at approximately 1.2 volts. So that's why your nickel metal hydride battery is somewhere in the 1.2 volt range. What we did when we moved to lithium batteries, we found non-aqueous solvents, meaning there is no water in a lithium battery. The minute you were able to do that, you were able to increase that window to approximately 3 times the window we have on a nickel metal hydride. When you triple the window, you triple the energy. So that's essentially what happened. We were able to go from a system that was stuck at a 1.2 with some amount of energy density to something that was a 3.7 volt system with a tripling of energy density.
But the electrolyte in a lithium battery is still a liquid?
It's a liquid electrolyte consisting of a lithium-based salt and a solvent.
And so the batteries that are in our laptops, for instance, are, in fact, we're carrying around some liquid?
Yes.
Which is,
yes.
I guess I had some sense that it was all solid state.
Right. So
that's not
you will see this term called a lithium polymer battery, where presumably the way they are selling it is as if it is completely a solid state polymer battery. It turns out that as of today, we do not sell polymer batteries in these markets. There are actually people sitting in this audience I can see who are actually working on making a polymer battery happen. But they haven't yet reached a point where you can put it in your laptop or your cell phone. When people talk about a lithium polymer battery, they're talking about what is called a gel battery. It's like jello. The electrolyte is sitting in the pores of this matrix. So presumably when you take it out, you don't see wet electrolyte falling down. So that's what they call a polymer battery today.
You mentioned that the progress rate, for lack of a more technical term, is about 5% a year in batteries. Is there a fairly accessible description of something that has been done that can tweak a lithium-ion battery and get that 5%? What would be an example of how you can improve on the current batteries?
So meaning that how do you go from 5 to 10% improvement, you mean? Or?
Well, you were saying that each year we're getting a 5% improvement.
Correct.
So why is there are these primarily manufacturing issues, or are they new chemical reactions or new chemicals introduced into the battery itself?
So the 5% was literally the comparison to Moore's law. What I mean by that is they had a set of materials, they had a box, every year, people got better in removing the unwanted stuff from the box and putting more and more of the active material into the box. So remember, a battery has an anode and a cathode, but it's got a big gap between the two of us so that we don't touch each other, right? Because we short with each other when we touch each other. This gap you have to keep reducing. And if you reduce the gap more, you pack in more of us, which is the active part of the battery, right? So that's what they did for many, many years. Recently, what we are seeing is a change in the cathode itself to newer cathodes. And if you go and look at the evolution of the battery curve, it's not a constant 5%. There are actually bumps that happen. When the bumps happen, some event has occurred. So the first bump, interestingly enough, happened in the late 1990s when the Chinese started entering the battery market. Then the Japanese realized they had to ramp up and make a better battery, so they actually found ways to pack in more. We're able to get a step change in the evolution of batteries. Today, the step change is happening because we're finding new materials. And frankly speaking, these new materials are going to be the driver for more change as we go into the future.
No, we have a lot of nanotechnology research that's done here, and the short take on nanotechnology is that as you get smaller, you have more surface area to work with per unit of stuff you're dealing with, and that surface area translates into chemical reactivity. So there are some good things that could potentially come from nanotechnology. I know there's nanotechnology battery research going on here. What's your assessment of where nanotechnology might play a role in improving the batteries that we're working on?
So that's essentially a mixed story when it comes to batteries. So we had great success in actually one material, which is called lithium iron phosphate. It turns out it's actually commercially available today from this company.
Lithium iron phosphate.
This company, A123 Systems, actually makes it. And there are other companies that make it also. In that particular material, we actually realized maybe 5 years ago that making it into a nanoparticle is the only way to make it work. And it's more than just a surface area effect, as it turns out. You actually change more than just the surface area. Thermodynamically, there are some differences that appear to be happening. So that material is a great material where, in batteries, nanotechnology was able to make a big difference to a particular material. But it turns out, in general, surface area is not a good thing. So batteries are always operating at places where they don't want to be at. What I mean by that is, think about lithium battery, right? I mean, we're talking about very large potentials. Lithium is a kind of species where it's so reactive, it wants to react with everything. And so it turns out that in most batteries we use today, there are all these side reactions that occur, reactions you don't want, that actually kill the battery. They actually lead to safety problems in batteries. And these reactions happen on the surface of these particles. So the more surface area you actually have more of these reactions. So you have to kind of control them very carefully. So if you go nano, there are some advantages, but there are also disadvantages in going that way. So for battery people, we've been very carefully picking and choosing the kinds of materials we want to go nano, recognizing that it may not be the perfect solution for all our problems. So it's not the panacea. It appears to be more of a sort of one more tweak and one more knob we can turn to see if we can get something a little bit better than what we have.
As sort of the host of this show, I'm allowed one really stupid question. And
am I allowed one stupid answer also? I've probably already made it, but.
And so I'm wondering about microelectronics, and there's this device called a capacitor.
Yes, sir.
And a capacitor, as I understand it, builds up and holds a charge. So I'm thinking, well, why can't we make lots of little capacitors and gang them all together and call them a battery? Why not?
You probably should become an electrochemist at some point. So it turns out there is something called an electrochemical capacitor. So what you do in an electrochemical capacitor, it turns out when you take any electrode and you put it in an electrolyte and you put a little bit of current to it, the first thing that happens is there are electrons that reach the metal and there are ions that come to the surface and they sort of stack up. And that stacking up is literally like a capacitor, like a dielectric capacitor that you see everywhere, right, in electronics. Except that this happens because of electricity in terms of an electrochemical cell where there are electrons and ions. We call that an electrochemical capacitor. Turns out their surface area matters because you're forming the double layer on the surface of these particles. The more surface area you have, the better. So electrochemical capacitors are a class of materials that are actually made. But think about it, right? It turns out that if you do the calculation, and maybe this is not something obvious when you just think about it, it turns out that the amount of energy density in an electrochemical capacitor is considerably smaller than that for a battery. So to give you a comparison, a battery has 200 watt-hours per kilogram. That's typical lithium-ion battery that you have in your cell phone. A capacitor would be maybe 5 or 10 watt-hours per kilogram. I can try all I can.
So they're just not in the same league.
They're not in the same league. Okay. They are fantastic as power devices. because all you have to do is you have to move the ions a small distance, nanometers, and boom, your energy comes out. And so as a power device, it's fantastic. So I kind of joke about it saying, if you put it in a car, you can go 0 to 60 in half a second, but then after half a second, you have no more juice left to stop. So that's basically the problem.
So we have some of the metrics. We have safety. We have energy density. Another issue is life. I'm often struck by how we almost impart a metaphor of living things to batteries. The batteries have a life, and when they're done, they die. So I'm just kind of curious as a word guy about that. But why is it that batteries have a life? Why don't they last forever?
Well, okay. So it turns out capacitors actually are the ones that probably are going to last a long time, because it turns out when you have a reaction, remember what I said, right? We're trying to use materials that have very high voltages. By definition, what we are doing is we want to have higher and higher energy because we want to pack in more things and have smaller cell phones or longer talk times in our cell phones, which means that we keep pushing that window. When we push those windows further and further, bad things want to happen. And so these bad things are side reactions that are things that are going to come back to kill the battery. So it's a choice that we've made that we need high energy, we need high voltage, and therefore we're willing to live with the fact that we have these side reactions. The side reactions will kill the battery. All we can do is manage the side reactions to the point where we get the 3 years or 4 years or whatever it is that you need, and then the battery dies and you move on. It is actually a choice. You can make a battery that lasts a long time. It's just a battery that will have so poor energy density that you may not want to buy it. That's the problem.
So essentially you're describing a kind of an engineering problem rather than fundamental science.
No. This is a fundamental science problem. Let me change that. Certainly you can find materials that don't have this problem. But in any realistic material that any of us want to use, this is a fundamental challenge. Thermodynamically, you will not be able to make any of the batteries we make today unless something changes in the way we do them. Unless we change the material set, we cannot have batteries that don't have side reactions. And if you have side reactions, by default, you are talking about something that is changing in the battery. And that change is going to come back to bite you at some point.
One of the questions that I hear most often from people, if there's a discussion about batteries, there seems to be something about batteries that intimidates people. I mean, one is that these things die on you. It's like, like a house plant or something. And the other is that that batteries have these weird traits, or at least some of them have these weird traits that they have memories. And that's very intimidating to think, oh, if I don't charge my battery at 100%, at the beginning, I'm going to end up with a battery that's a half a battery the rest of its life. I mean, these are terrible things. Why do these things happen?
So memory effect is a very specific to a particular chemistry, nickel-cadmium. It doesn't exist in any of the other chemistries. It's a very curious trait of the cadmium electrode and the way the electrode actually operates, that it actually nucleates a phase, and that's the reason it occurs. But you bring up actually a larger point, which is, I think most of us kind of obsess about the batteries that we do have. We want to see them last longer. We want to make sure that there is enough juice left in them, and we're always asking questions like, why is the battery failing? And this is a constant thing. And my dad, who lives in India, and he's an engineer, but nothing to do with batteries at all. I remember him calling me. This was probably 10 years ago. He was talking about how his cordless phone batteries were dying. He wasn't getting much juice from them. Those use nickel metal hydride batteries. Or nickel-cadmium batteries during those days. And he kept asking me what was going on. And I said basically something like, just throw that battery and get a new one. I mean, why are you paining me with this? So he calls my brother, who then goes on the web, does a Google search, finds out there is a memory effect, tells my dad to go and put a resistor on the battery so that he discharges completely and charge it back up, and the thing comes back to life. So I got a phone call from my dad saying, what exactly are you doing in battery research? Because your brother is able to answer this question, right? So I'm sitting there thinking, this is great, right? So, but I mean, my dad actually obsesses with his batteries. I mean, he bought a UPS pack, and he's all concerned about exactly how he should charge and discharge the batteries. And it turns out that there are things you could do to make your batteries last longer. And if you understand the chemistry in the battery, there are tricks you can play to get the batteries to go a little bit longer. For most of you using cell phone or laptop batteries, the trick is to what I call pulling the plug, meaning don't keep your batteries completely charged. If you keep them completely charged, these side reactions I'm talking about come back to bite you. So when the battery is fully charged, just remove the plug, let the battery discharge a little bit. Don't use a laptop like you use a desktop. Just if you don't do that, you actually have a huge advantage in these batteries. They actually last longer.
The topic here is the future of batteries, and I did my homework, or at least tried to, and every article that I read about the future of batteries talks about how we're in this lithium-ion world right now, and that the goal, that the holy grail of battery research is the lithium-air battery. What is the lithium-air battery, and how soon can I buy one at my store?
Tomorrow, if everything goes well. But so a lithium-air battery is depending on how you want to sell this, it's a battery electrode on one side and a fuel cell electrode. I don't know if you know what a fuel cell is. It's the oxygen-hydrogen reaction fuel cell on the other side. So essentially, you have lithium on one side, and you have oxygen from the air coming into the other side, and it reacts.
So the oxygen is the cathode?
The oxygen is the cathode, and the lithium would be the anode. And then they react, and you form a product. In this case, lithium and oxygen combine to form a product. And the hope is that you can recharge that product, and then oxygen goes back into the atmosphere. The nice thing about this is you don't have to carry around your cathode because the oxygen is coming from the air. You only have to carry your lithium, so people like that a lot.
So it's lighter weight.
It's lighter weight. I mean, if you think about a typical battery, right? I mean, the only prop I bought is a battery that essentially, this is all the batteries that you have in the world, right? These are a lithium battery. It is made here at the lab. It's a small prototype. And you sort of make bigger and bigger one of these, and you make a lithium battery. This is a box, meaning all the reactants are inside the box. When my car runs out of juice, it doesn't matter. The box, I still have to carry it back to the charging station, right? The product stays in the box. But the beauty of an oxygen cell would be I can get the reactant from the air. The product stays in the box, but hopefully the fact that the reactant is coming from the air allows me an advantage, right? So it turns out if you do the calculations, on paper, the theoretical energy density is pretty significant. It's actually approaching things like gasoline. So there's a lot of excitement about that chemistry. But the chemistry is very hard to play with. It's not even obvious to us that it's a rechargeable chemistry.
If you were to describe, say, 3 big hurdles facing the lithium-ion battery, in order of
lithium-air battery, you mean?
Lithium-air battery, excuse me, I misspoke. What are the biggest hurdles?
So I should be careful because this has been televised. So, so you have to first prove to yourself and to everybody else that this is really a rechargeable battery. There are a lot of batteries in the world that don't recharge. We actually have alkaline batteries that don't recharge very well, and that's perfectly fine. But for the purposes of this, this talk, we are talking about rechargeable batteries, things that can reversibly go back and forth significantly. We have to prove to ourselves that it is rechargeable, and it's not obvious that it is. The second thing we have to do is we have to prove to ourselves that even if it's rechargeable, it is something that will be recharging at good reversibility, meaning it turns out that you may lose a lot of energy that you put in, you may not get it back out. Nobody wants that. You don't want a lot of energy going and not coming back out, and that's a significant challenge in this chemistry. The third challenge, and this is actually a big challenge, is remember, this energy density we're talking about for lithium air is on paper, meaning it's a theoretical value that you calculate on a computer. Practically, when you actually make a real device, things can look very different. And people sort of don't recognize that in the battery space. Like I said, right, you should try making a battery. It's a very humbling experience. I took a sabbatical from the lab 3 years ago to work at a startup. And I wanted to really go make a battery for myself, right? I'd worked on batteries for many years, and I thought I knew a lot about it, but I wanted to go do it. And it's a humbling experience. I mean, you sit down and you realize how hard it is.
We should have brought the potatoes and the limes.
Oh, yeah, that'll work much better, I think.
We could have done that, right? Now, you are working on something, I think, through ARPA-E on a flow. Is it the flow battery?
Yeah, we're working on a flow battery.
Tell us briefly what that is, and then we're going to open up the floor to questions.
Okay. So essentially, not all batteries are the same. And every battery has to be, you have to pick a battery based on the application that you're going after. So it turns out that when we first heard about sort of multiple markets in the world, right? There's an electric car market where we're all talking about lithium batteries and maybe lithium air or one of those chemistries. But if you're trying to store a lot of electricity from the grid, so let's say you have solar panels that you want to store electricity during the day, use it during the night, then space is not a constraint. Hopefully in the US, all of us have big spots everywhere where we can store stuff. And so you remove a huge constraint from the vehicle battery, which is that you have only a certain amount of space to pack things. So you can start thinking about other kinds of chemistries that we are not thinking about at this moment. And one of the things that we're doing is a flow battery, and this is my second prop. So this is essentially how a flow battery looks. This is sort of an older version of it. So for those of you can see, there are all these tubes that you can actually fit pipes in. So the way the flow battery works is that you could think of this as your internal combustion engine. It's like it's like your internal combustion engine where the reactions occur. You have a separate gasoline tank. In this case, it'll be a flow battery reactant tank. The reactants will come through into this chamber here. They will react. The electrons will be given out, and the product goes out and you put it in a separate tank. And so you can then take the product, come back into this thing, and you can charge it, and then you can take it back and you can discharge it. What that means is that you're sort of separating energy and power. This is your power cell. The tanks are your energy cell. And the beauty of this is you can actually store a lot of electricity because space is not a constraint for you. And the beauty is you can make it very cheap. And cost is a very important metric in batteries, especially when it comes to grid-scale storage. So our hope in this project is to actually make something that we believe is going to be an extremely low-cost cell. It turns out that there's a very big difference between these two kinds of batteries. And you can't appreciate it here, but I would urge you to come and see our labs. It's in Building 70. We have lithium battery things that one of my colleagues in the lab builds. And these are very small devices, they, essentially this size or even smaller sizes. And then you'll go to a fume hood. The whole fume hood is filled with this device and a few auxiliary tanks and pumps and all that. In order to do the same experiment in a flow battery, you need a lot of space. And you sort of appreciate how the scales are very different from each other. So it's a different project, and it's for a different application.
So let's see if our audience has any questions. Just raise your hand.
Okay, so we've talked a lot about how a battery might compare to an ICE and how we might try to make a battery fit into pre-existing ideas. But what could be done with battery just as is? What might be an idea of a different type of entry market that a battery could satisfy just right now?
What do you mean? Meaning, if you have a battery company, where do you go sell the battery today? Is what you're asking? Or?
Yeah. So instead of trying to put the batteries into cars, part of it reminds me of trying to make a veggie patty taste like a burger. Like, you're trying to make it do something that there's already a pre-existing competitor. But if you were to maybe branch into a different arena or a smaller market, try something.
So I'm not going to let me give you I'm going to give you the answer in two parts. If you start a battery company, probably where you want to go sell your batteries is consumer electronics market. You will not be selling it to the vehicle market because there is no vehicle market. That's just the reality of how batteries are. But let me change the answer to addressing your specific question. If I have a battery company and I'm motivated to actually sell to the vehicle market, I'll probably go after the fleet market. A market that is defined, a market where I don't have to worry about range anxiety of people, the fact that I might be stuck in the freeway without without being able to charge the battery, without having to understand how to manage the battery pack. Some place where there is a centralized unit which can take care of all those things. That is where I would go first. In some sense, it's very similar to fuel cells, which you certainly know quite a bit about. And so you're sort of going after a market where you think that you can manage all the problems with these things. And then hopefully your learning comes up, you understand more, and you start going towards the real market that you're after, the electric vehicle market. And there are a lot of people essentially trying to do that, starting from these smaller buses and fleets, and then slowly moving towards the mass market. Selling to the public has its own set of challenges. And maybe selling to the public directly is not the best way to start.
I'm wondering what percentage of the energy used to recharge batteries is lost in discharging them, in particular in the lithium-ion and in your flow battery.
Got it. So in a typical lithium-ion battery, you can get as much as 95% energy efficiency. You lose 5%, okay? Turns out that how much you lose depends upon how quickly the power is what matters. If you pull the energy out quickly, you lose more. If you pull the energy out slowly, you lose less. But battery people will say lithium battery is 95%. More than 90% is easy for us. Flow batteries, on the other hand, are very different. The flow battery we are trying to use, we're shooting for 80%. We'll see if we get it. Again, in flow batteries, you have the same problem. It depends upon the rate at which you're pulling the energy. But typically, most battery people, we talk about 70, 80, 90%. If somebody tells us it's 50%, forget it. We're not interested. So not to take a rap against fuel cells, but when we talk about fuel cells and fuel cells that are 50%, round trip is probably 35. For people in the battery world, that's a very small number. I mean, we want to be up in the 80, 90 numbers.
How long do you think it's going to be before we can see batteries being used for, cargo ships and airplanes?
Actually, that's a huge, especially the airplane travel is a huge challenge for us going forward, right? I don't know. I mean, we'll probably use it in, locomotives use batteries in HEV mode, meaning small batteries that sort of give someone a little bit of input at various times. I could see that. I could see batteries sort of being an auxiliary. I don't believe that it's ever going to be a primary source. I mean, I can't imagine that. The energy density differences are just so huge. I just cannot see that happening. It's a huge challenge. I mean, we've got to come up with some sort of a fuel that allows us to do all those things. I just don't think it's going to be a battery pack. I hope I'm proved wrong, but it's hard for me to see that.
I had heard that the lab was talking to other labs and collaborators about an energy innovation hub for electric storage. And I was wondering if you could maybe comment on that. Would Berkeley Lab lead a collaboration? Have proposals perhaps been submitted to the department?
So I should be careful, only because we are at a sort of at a time when I think the FOA is, I mean, the Department of Energy is talking about trying to issue an energy storage hub. So these things come about because the Department of Energy issues a hub, and then we all go respond to it. Certainly, that is, if the Department of Energy issues a hub, I think Berkeley Lab will be very, very interested, only because we have one of the largest battery programs in the country, and obviously we will want to see us doing something about it. So we certainly are very interested, and we're talking, but I probably shouldn't say more than that. I apologize.
I have a question while
Yes,
we're waiting for more questions. You are somewhat unique in that you've been blogging about batteries. And how has that affected your work, other than the fact that now the New York Times calls you?
Me, yeah. So, it's been an interesting experience. I have the reason I did it is because of people like Dan and Julie Chow and Doug Isabel, who they literally were just hounding me to do something. I mean, not to offend them, but and I'm really glad they did. I mean, my wife sort of knows this. I've never had a hobby really, and this has become kind of a hobby for me. When I have time on a weekend, I sit down and write a blog. I haven't written one in a couple of months. I've been busy with something else, but it's actually been a really fun experience. And part of the reason why I love it is because you have to be able to explain what you do to a general audience. I mean, I think it's sort of very important to do that. And it's a challenge. I mean, to be able to stand there and frankly, it's a whole world. Anybody can comment about these things, and they come from a completely different angle, and it's sort of fun, sort of listening to all these things happen. And even for myself, I've thought about Moore's law and batteries, but never really with a focused attention. But when you have to write 300 words about that sort of really sharpens your thinking, and you go and write something that you think is what you believe is really happening. And to me, it's been personally a very satisfying and a wonderful experience. Highly recommend it. You make no money out of it, but highly recommend it.
We have a question in the center.
Right here. So you kind of talked about those flow batteries as kind of potential for energy storage for like off the grid or something like that. What kind of energy densities can you get with those now, and what kind of energy densities do you think are attainable? Because I mean, you can see a direct analogy to using that as in place of gasoline if you could have a high enough energy density, right?
Right. So it's very appealing when you sort of think about it in that fashion. Turns out, theoretically, it sounds very appealing, right? So the energy density of most of these flow batteries are very far from lithium batteries. I mean, you're probably talking about 40, 50 watt-hours per kilogram instead of 200 watt-hours per kilogram, right? And you're typically limited by sort of the solubility. It's a molarity problem. How much can you take? And essentially, it's not a very large amount. And so you have to have big tanks. Bigger the tank, the more space, and that becomes a huge challenge. That is not a fundamental problem. I think it's just where we are in what we know today in terms of the molecules that we use. Certainly, I think what you're articulating is a very logical research path, is saying, can I find molecules that actually have the kind of energy density that will allow me to get very large numbers? And can I then use it in this flow configuration? Because one of the beauties of this is you can separate the charging time problem, right? That's the biggest thing that everybody talks about. You discharge your battery for 3 hours, and then you're charging it up for 8 hours or 20 hours, depending upon the battery that you buy. That eliminates the problem. You can go to a gasoline station or a flow battery recharging station, boom, you just take out the spent tank, put in a new tank, and you're off and going. And it's a very appealing thing. We're just not there yet. I think it requires more attention before we can go there. You might have seen something from, I know that you're in the battery space, from Edming Chang, where they're sort of thinking about that issue. So there are people talking about it and thinking about it. So.
I was going to ask, so with this new kind of advent of nanotechnology and how it kind of allows us to kind of exploit quantum mechanics in a new way, I'm just kind of curious how batteries kind of, if that kind of new exploitation kind of can be applied to batteries in any way, and if it already has been, because I know nothing about new battery technology. So I'm just kind of curious if our ability to kind of exploit quantum mechanics and that kind of stuff with new nanotechnology is kind of
I couldn't hear your question very well. Did you say quantum mechanics?
Yeah.
Okay. I'm going to change the question slightly. I mean, I think what I'm going to ask myself, I think the question I think you're trying to ask is, can you use sort of a theory as a means of predicting where batteries are going to go and evolve? Would that be a good way to describe the question?
Can you use quantum mechanics to make more efficient batteries, I guess?
You can certainly use computational tools to make more efficient batteries. Actually, there are existence proofs that you can use DFT. Even at the lab, we have people who've used DFT to calculate new materials that could be used in battery applications, and they've had reasonable success with it. That certainly is something you can do, is being done a little bit, and certainly more has to be done in that area, I think.
A question over here.
Yes, my understanding is that the greatest deposits of lithium that we have available to us are in the Atacama Desert in Chile. If we begin to really ramp up using lithium batteries, how long before that resource will become depleted?
So people have done some analysis, and I guess I'm probably not the best person in the world to talk about the politics of how the lithium space is going to play. But it turns out that at least for the foreseeable future, we don't particularly have a problem if we continue to use lithium. Let's say there's a rapid ramp up in electric cars with lithium. Then you have a flow problem, meaning you have to build up the sort of this infrastructure to get out of lithium. But I suspect that that's not going to happen, right? I mean, it's not as if electric cars are going to suddenly come into the market. It's going to be a slow, steady increase in the ramping. So my suspicion is that we'll be able to keep up with that. The other extreme is what happens if every car in the world is made into a lithium battery car. I mean, yeah, there certainly is a lithium problem if that happens. But people like me sort of joke about it, saying if you ever get into a point where we are really worried about it, we're probably in a much better space than we are today. We actually have electric cars. We're sort of using that. And so I don't believe that it's a problem right now. I believe that you have to think about these other things, and we certainly are thinking about other things. But it's not that's something that we have to do today and worry about it today.
Then, could I have a question about energy density, and going back to the issue of are we just swapping coal burning for gasoline? Isn't there some inherent efficiency in an electric motor that is better than a gasoline engine in that a lot of gasoline, although it has all that energy density, an awful lot of it is wasted?
Correct.
Whereas if we had a coal-fired system of feeding energy into our cars, there would be less waste. Is that accurate? Maybe not.
I don't know the answer to that question. I mean, obviously, everything has an efficiency. I'm thinking of it as CO2 coming out, right? So you have CO2 coming out of your gasoline car, So it's not efficient, but what matters is how much of what is coming out of the tailpipe. And from the coal-fired plant, obviously, you have CO2 coming out. I guess that's the fair comparison. I guess my understanding was that it's like the questioner asked. It is better to, if you have a coal-fired plant, making a PHEV makes no sense. I think that people have concluded that. I think
we have time for one or two more questions.
I think we have one up here.
Hi, I don't know much about batteries, but I know that at a national level, and especially in the West, there's a concern for being able to respond to peak power loading on the grid level. And I was just curious. I hadn't heard about the flow battery technology you're speaking of, and I'm just curious. Do you see that being able to be scaled to a level where you can have battery banks that are able to store energy during off-peak periods and then release that and make that accessible during peak power loading periods at a grid level?
Right. So part of the RPE project we have is grid-scale storage. It's storing large amounts of electricity. Certainly, the grid is not one single application, right? I mean, the time of storage, meaning time of discharge, seems to vary from milliseconds all the way to many hours. Flow batteries probably make the most sense if you're storing flow batteries we are thinking about today. Let's not talk about the future. Are probably make the most sense when you're storing electricity for maybe 7 hours, 8 hours, maybe down to 5. They probably make no economic sense if you're trying to store them for, say, 1 hour, right? So you have to think about other kinds of batteries if you were to do that. At the lab, we're looking at all those aspects. I mean, it is a pretty complicated market. If you know the grid space, you probably recognize it more than I do, that it's a pretty complicated market. And the kinds of batteries we would use for these different markets will be different. And flow batteries have their place, but they are not going to be the solution for all of those applications. They will be a solution for some applications that require more than maybe 5 hours of discharge, where you're storing electricity for that kind of time frame. More the hours, the better the flow battery would be. So,
as we wrap up here, I want to point out that there's an awful lot of interesting science and research going on in this lab, and at this very place, at this very time, next Wednesday, Margaret Torn is going to be talking to us about the carbon cycle, some very interesting research and new ways of looking at the carbon cycle. I think it'll be a very fascinating discussion, and I encourage you to encourage your friends to come to these events, and I'm hoping that you enjoy them. I want to thank Venkat Srinivasan for a very, very interesting hour. Thank you.
Thank you.
And I also want to thank you for coming here and for your insightful questions.